Fine. Let's start. Number 10. The signal from nowhere. In 2003, a network of volunteer computers running City at Home flagged something strange. A radio signal at 1420 megahertz, picked up by the Arecibo telescope in Puerto Rico, coming from a patch of sky between Pisces and Aries. 1420 megahertz. That's the hydrogen line, the frequency at which the most common element in the universe naturally absorbs and emits energy. If you were an alien civilization trying to pick a channel that anyone with a radio telescope would be monitoring, this is the one you'd choose. It's the cosmic equivalent of dialing 911. The signal was detected 3 times. Total observation time across all 3 detections, less than 1 minute. SETI's chief scientist Dan Wertheimer called it the most interesting signal from SETI at home. And then, the project quietly distanced itself from the media coverage that followed, but here's the thing. The direction it came from, there's nothing there. No stars within 1,000 light years, no planets, no galaxies, just empty space. And the signal's frequency drift was far too rapid for any known astronomical source, too fast for orbital motion, too fast for stellar wobble, too fast for anything we have a name for. No telescope has detected it since. Breakthrough Listen has scanned the region. Nothing. The signal hit the perfect frequency from a place with nothing in it 3 times and then stopped. Somewhere between Pisces and Aries, something spoke once. And whatever it was, it didn't feel the need to repeat itself. Number 9. The signal that won't be named. In 2020, astronomers using the Australian Square Kilometre Array Pathfinder were scanning the center of the Milky Way when they found a radio source doing something they couldn't categorize. It was switching on and off with no pattern. Sometimes it stayed bright for weeks, sometimes it vanished in a single day, and its light was circularly polarized, meaning the radio waves were corkscrewing through space as they traveled. That last part matters. In a typical radio observation, you might scan thousands of sources. Maybe 10 of them will be circularly polarized. It's rare. This one was among the most polarized and most variable sources ever found, which is a strange combination. Variable things tend to be chaotic, polarized things tend to be orderly. This was both. The team tried to match it to every known category of radio source: pulsar, flare star, galactic center, radio transient, X-ray binary. They checked for counterparts in X-ray, infrared, optical. Nothing at any wavelength except radio. The lead researcher, Ziding Wang, published his conclusion in about as honest a sentence as you'll find in a scientific paper. We came up with several interpretations, but none of them can really fit well. That's not a mystery wrapped in hype. That's a scientist saying, plainly, we tried everything, and the answer is, we don't have one. The source is still there, still flickering, still unidentified, still pointing back from the center of the galaxy like a light nobody left on. Number 8, the signal that almost never was. On July 24, 2001, the Parkes Radio Telescope in Australia recorded a 5 millisecond flash of radio waves, a burst so brief you could miss it in a heartbeat. Literally. Your heart beats in about 800 milliseconds. This thing was over 6 times faster. Nobody noticed. The data sat in an archive for 6 years. In 2006, a professor named Duncan Lorimer at West Virginia University assigned an undergraduate student named David Narkovich to look through old Parkes data as a class project. Week after week, Narkovich would meet with Lorimer for an hour, reviewing what the software had flagged. Most of it was interference, known pulsars, noise. Then one day, Narkovich found something that didn't fit any category. A pulse at a dispersion measure of 375. That's a way of measuring how much interstellar gas the signal passed through on its way to Earth. And 375 was way too high for anything in our galaxy. This thing came from cosmological distances, billions of light years away, and it was bright. Absurdly bright. So bright it had actually saturated the detector, and the telescope's own software had flagged it as an error and buried it. The Lorimer burst, as it came to be known, was roughly 10 to 12 orders of magnitude brighter than any known radio pulse. That's 1 trillion times brighter in 5 milliseconds. And then things got worse. A researcher named Sarah Burke Spolayer went looking through the same Parkes archive and found signals that looked suspiciously similar. Swept radio bursts at similar dispersion measures. Except these turned out to be caused by people at the observatory opening the microwave oven door before it finished running. The leaking radiation produced signals that mimicked what Lorimer had found. For years, the Lorimer burst lived under that shadow. Was it real, or was it a microwave oven? It took until 2013 for another team to find 4 more bursts like it. Different telescope, different sky, same kind of signal. They coined the term fast radio burst. FRB. And just like that, the thing a student almost missed in a pile of old data became the founding event of an entirely new branch of astrophysics. Thousands of FRBs have been detected since. We've traced them to galaxies billions of light years away. We've used them to find missing matter in the universe. And the one that started it all, the Lorimer burst itself, has never repeated. The biggest discoveries don't always announce themselves. Sometimes they hide in the reject pile, waiting for someone patient enough to look. Number 7. The signal on a schedule. 500 million light years from Earth, something is keeping time. FRB 1800916 was detected by the CHIME radio telescope in British Columbia starting in September 2018. It's a repeating fast radio burst, which by itself isn't unique. A handful of FRBs repeat. What made this one different was the pattern. It fires for about 4 days, then it goes silent for 12, then it fires again. A 16.35-day cycle observed continuously for 409 days. 38 bursts all arriving within the same 5-day window of each cycle. This half of them clustered into a window of just over 14 hours. That's not random. That's a schedule. The source was traced to the outskirts of a spiral galaxy sitting in a star-forming region. The immediate assumption was orbital, something in a binary system where one object periodically blocks or modulates the other's signal. Maybe a neutron star orbiting a massive companion, its bursts obscured by stellar winds during part of the orbit. But here's the thing. A second, repeating FRB 121102 was later found to have its own activity cycle. 157 days, 90 days on, 67 days off. That's 10 times longer than FRB 180916. Whatever mechanism drives these schedules, it might not be the same for both, and no model proposed so far can explain both cycles simultaneously. Even 500 million light years away, across a distance so vast that the light we're seeing left before complex life existed on Earth, something is following a rhythm. It doesn't care that we're listening. It was doing this long before we were here. It will keep doing it long after. Number 6. The call from next door, April 2019. The Parkes telescope in Australia is pointed at Proxima Centauri, the nearest star to our sun, 4.2 light years away. Close enough that if you could drive there at highway speed, it would only take about 50 million years. The Breakthrough Listen project is running observations, 30 hours of data collection over the course of a few weeks. The data goes into a pipeline and sits there until an undergraduate intern named Shane Smith starts processing it in the fall of 2020. And he finds something. A narrowband signal at 982 megahertz. Narrowband means it occupies a tiny sliver of the radio spectrum, the kind of signal that natural sources almost never produce. Technology produces narrowband signals. Stars don't. The signal appeared only in the on-source observations when the telescope was pointed at Proxima Centauri. It vanished in the off-source observations when the telescope was pointed away. It persisted for more than 2 hours. And it drifted in frequency, exactly the way a signal would if it were being emitted by something moving, like a planet. Except the drift went the wrong direction. A signal from a planet orbiting Proxima Centauri, given Earth's rotation, should have drifted downward in frequency, like a trombone sliding lower. This one drifted upward, like a slide whistle. The Breakthrough Listen team named it BLC-1. Breakthrough Listen, Candidate 1. The first signal in the project's history to pass every initial filter, Andrew Semyon, the project's principal investigator, called it the best candidate signal they'd ever had. And then they tried to figure out what it actually was. They checked licensed transmitters near the observatory. Nothing at 982 megahertz. They checked satellites, aircraft, asteroid reflections. Nothing. They checked whether the telescope was pointed at a nearby building, the visitor center maybe, or a car on the highway. Nothing. They checked the temperature logs of the instrument room. They checked the observatory's internal chat logs for any unusual events. Nothing matched. After 2 years of analysis, Sophia Sheikh led the team to a conclusion. BLC1 was most likely terrestrial radio frequency interference, an intermodulation product of multiple local electronic signals that happened to align with the observation cadence. They found dozens of similar ghost signals at harmonically related frequencies, but they never identified the specific source. No device, no transmitter, no piece of equipment. They know what BLC1 probably was. They just can't point to the thing that made it. It remains the most deeply interrogated signal of interest in the history of the search for extraterrestrial intelligence. The closest we've come from the closest star. And the answer is probably us talking to ourselves in a frequency we didn't know we were using. Number 5. The Galactic Center Phantom. September 30th, 2002. A team of astronomers from Sweetbriar College and the Naval Research Laboratory are monitoring the center of the Milky Way at 330 MHz using the Very Large Array in New Mexico. Over 7 hours, they detect 5 radio bursts. Each one lasts about 10 minutes. Each one is roughly the same brightness. And they arrive every 77 minutes, like clockwork. The source, designated GCRTJ 1745-3009, sits about 1 degree south of the galactic center. That's close. Cosmically speaking, that's in the front yard, and the bursts it was producing were extraordinary. If the source was actually at the distance of the galactic center, around 26,000 light-years away, its brightness temperature would be on the order of 10 to the 16th Kelvin. That's 10 quadrillion degrees. In a source compact enough to change in half a second, meaning it was smaller than our sun. Nothing visible at that location, no X-rays, no infrared, no optical counterpart, just radio bursts ticking like a metronome. A year later, in September 2003, they caught it again. 1 burst, 3 times weaker than before. Then in March 2004, 1 more burst, 30 times weaker, lasting only 2 minutes instead of 10, and with a spectral index of negative 13.5. For context, most radio sources have spectral indices between 0 and negative 2. Negative 13 is off the charts. Almost all the energy was crammed into the lowest frequencies. The proposed explanations read like a list of increasingly exotic physics. A precessing pulsar with an unusually wide beam, a white dwarf pulsar, which shouldn't exist. A double neutron star binary. A quark star, which is entirely theoretical. None of them fit all the data. And then the source went dark. It hasn't been detected since 2004. Something near the center of our galaxy turned on, pulsed 5 times with mechanical precision, flickered twice more while growing fainter, and then disappeared. We pointed every telescope we had at it, we found nothing, and 20 plus years later, we still have no idea what it was. The galaxy keeps its secrets close to its heart. Number 4. The 18-minute lighthouse. In 2020, an undergraduate student at Curtin University in Australia named Tyrone O'Doherty was given what sounded like a fun project. Look for radio sources that are changing in a large survey of the southern sky. By the end of the year, he'd found something unusual in data from early 2018, a source that appeared, blazed for a few months, and then vanished. These things happen. Sources appear and disappear. They're called radio transients, and they usually point to something dramatic. An exploded star, a collision, something violent. His supervisor, Natasha Hurley Walker, started investigating, expecting something familiar. What she found was anything but. The source, cataloged as Gleam, XJ 162759.5-523504, pulsed every 18.18 minutes. Not milliseconds, not seconds. Minutes. That shouldn't happen. Pulsars, the rotating neutron stars that produce regular radio pulses, spin fast. The slowest known pulsars complete a rotation every few seconds. Most do it in milliseconds. An 18-minute rotation period is hundreds of times slower than anything in the known catalog, and yet this thing was blindingly bright. During its active period from January to March 2018, it outshone every other source in the field. Supermassive black holes, flaring jets of matter at nearly the speed of light. This was brighter. Its pulses were almost completely polarized, meaning the radio waves were all vibrating in the same direction, a hallmark of an intensely magnetic source, and the pulses change shape in half a second, which constrains the source to something smaller than half a light second across, much smaller than our sun. When the team first saw what they had, Hurley Walker later described the reaction on their Slack channel, colleagues posting, "It's repeating too slowly to be a pulsar, but it's too bright for a flare star. What is this?" Followed by the alien emoji, she ran the numbers on whether it could be artificial. It wasn't. The broadband emission ruled that out. This was natural. But natural as in what? If it's a neutron star, it's spinning impossibly slowly. Current models say neutron stars spinning that slowly should have crossed the death line, the theoretical threshold below which a pulsar can no longer generate radio emission. This one apparently didn't get the memo. If it's a white dwarf, the dense remnant of a burned-out star about the size of Earth, the rotation period would make more sense. White dwarfs can spin slowly. But we've never seen a white dwarf produce coherent radio pulses like this. There's no accepted mechanism for it. It turned on in January 2018. It ran for 3 months. And then it switched off. Every telescope that's looked for it since has found nothing. A cosmic lighthouse that shouldn't exist lit up, swept its beam across our little corner of the galaxy, ran for 1 season, and went dark. We don't know what it was. We don't know why it started. We don't know why it stopped. And we have no guarantee it won't start again. Number 3. The signal from a dead galaxy. Everything we thought we knew about where fast radio bursts come from has a story. It goes like this. A massive star is born. It lives fast. It explodes as a supernova. It leaves behind a magnetar, an ultra-dense neutron star with a magnetic field a quadrillion times stronger than Earth's. That magnetar, in its violent youth, produces fast radio bursts. It's a clean story. Young stars, violent deaths, screaming remnants. And for years, the data backed it up. Nearly every FRB we traced to a host galaxy found its home in a region with active star formation. Young stars, young magnetars, young signals. In February 2024, the CHEAM telescope in Canada detected a repeating burst. 22 pulses between February and July. They designated it FRB 2024009A and used a new outrigger telescope to pinpoint its location. What they found didn't fit the story. The burst came from the edge of a galaxy 11.3 billion years old. Not a young active star factory, an ancient elliptical galaxy, a dead galaxy. One that stopped forming stars long ago. No young massive stars, no recent supernovae. No plausible way to produce a magnetar through the standard channel. And the FRB wasn't just in this galaxy, it was on the outskirts. 130,000 light years from the galaxy's center. Farther from its host than any FRB ever localized. Out in the cosmic suburbs where almost nothing lives. Tirane Eftekhari, a NASA Einstein Fellow at Northwestern who led one of the 2 discovery papers, put it simply. The prevailing theory is that FRBs come from magnetars formed through core collapse supernovae. That doesn't appear to be the case here. The leading hypothesis now is that the burst originated inside a dense globular cluster at the galaxy's fringe. Globular clusters are ancient balls of stars, tightly packed where exotic things can happen. Neutron stars can form not from supernova explosions, but from white dwarfs collapsing under accumulated mass, or from 2 neutron stars merging. Channels that don't require young stars at all. If that's true, it means there's an entirely separate population of FRB sources out there, not born from the deaths of young giants, but forged in the quiet ancient corners of the oldest galaxies, places we weren't even looking. Wenfei Fong, the senior author on both discovery papers, said something that stuck with me. Just when you think you understand an astrophysical phenomenon, the universe turns around and surprises us. The universe doesn't owe us a clean narrative. Sometimes the signal comes from the last place you'd look. Sometimes the retirement home has something to say. Number 2, the space roar. In July 2006, NASA launched a balloon from Palestine, Texas. Strapped to it was an instrument called Arcade. Absolute radiometer for cosmology, astrophysics, and diffuse emission. 7 radiometers. It immersed in more than 500 gallons of liquid helium, chilled to 2.7 degrees above absolute zero. The same temperature as the cosmic microwave background itself. That's not a coincidence. When your instrument is the same temperature as the thing you're trying to measure, your own heat doesn't contaminate the signal. Arcade floated up to 120,000 feet, where the atmosphere thins to almost nothing, and it listened. The mission was straightforward. Detect the faint radio heat from the very first generation of stars. The stars that ignited in the darkness after the Big Bang, hundreds of millions of years before the galaxies existed. Their thermal glow should still be out there, faint but detectable, layered into the cosmic radio background like a watermark. Arcade didn't find it. What it found instead was a signal 6 times louder than any model predicted. A wall of radio noise, uniform across the sky, too loud to be the first stars, too loud to be the combined hiss of every known galaxy, too loud to be gas in the outermost halo of the Milky Way. The team ruled out every source they could think of. Alan Kogut, the project leader at NASA Goddard, said, "The universe really threw us a curve. Instead of the faint signal we hoped to find, here was this booming noise 6 times louder than anyone had predicted." They announced the finding in January 2009 at the American Astronomical Society meeting. 4 papers were submitted to the Astrophysical Journal. The phenomenon was dubbed the space roar, though of course it isn't sound. It's radio synchrotron radiation. So charged particles spiraling around magnetic field lines, emitting electromagnetic radiation as they go. Every galaxy does it. Every active region in space does it to some degree. But here's the thing. Dale Fixon, a University of Maryland scientist on the Arcade team, pointed out a fundamental problem. Every synchrotron source produces the same spectral signature. The instrument can tell that the signal is synchrotron radiation. It cannot tell what's producing it. It's like hearing a hum in your house and knowing it's electrical, but being unable to find the appliance. Some researchers have suggested that perhaps there are far more dim radio galaxies than we think. Galaxies individually too faint to detect, but collectively loud enough to produce the roar. The math requires them to be packed so tightly that there are no gaps between them, which seems unlikely. Others have floated the possibility that synchrotron emission from the Milky Way's own halo is being underestimated, or that the first stars were far louder than expected, or that something about the standard cosmological model is slightly wrong at radio wavelengths. And here's the cruelest part. The space roar isn't just mysterious, it's obstructive. It's so loud that it drowns out the very signal Arcade was built to find. The heat from the first stars is still hidden behind this wall of unexplained static. We went looking for the universe's baby pictures and found them blocked by a sound nobody can trace. As of 2026, the space roar remains an unsolved problem in astrophysics. No follow-up mission has been flown. The instrument sits at Goddard. The roar continues. The universe is not silent. It's screaming, and we don't know why. Number 1, the wow signal. August 15th, 1977, a Tuesday. At Ohio State University's Big Ear Radio Telescope, a printout is spooling out data from an automated sky survey. Columns of numbers and letters, each representing 10 seconds of average signal intensity across narrow frequency channels. Blanks and low digits mostly. Background noise. The cosmic hum of nothing in particular. A few days later, astronomer Jerry Amont sits down to review the printout. He scans the columns, and then he sees it. 6EQUJ5. A sequence that spikes to U, which represents a signal intensity between 30 and 31 standard deviations above the background. To put that in perspective, a signal 3 standard deviations above noise is considered noteworthy, 5 is remarkable. If 30 is something else entirely. Iman circles the sequence in red ink and writes one word in the margin. Wow. The signal lasted 72 seconds. That's exactly how long the Big Ear telescope's beam would take to sweep across a fixed point in the sky, which means the source didn't cut out early or overshoot. It arrived, peaked, and faded precisely as a genuine celestial source would. Its frequency, 1420 MHz. The hydrogen line again. The same frequency as our number 10 entry. The frequency that SETI researchers had long theorized would be the most logical channel for interstellar communication, because hydrogen is the most abundant element in the universe, and any technological civilization with a radio telescope would know this frequency intimately. It's also a protected spectrum. Terrestrial transmissions at this frequency are forbidden by international agreement, though violations have been documented. Amon himself was cautious. In 1994, he suggested it might have been an Earth source signal reflected off a piece of space debris. He later walked that back when calculations showed the reflector would need properties that don't physically exist. In 2017, Antonio Paris proposed that hydrogen clouds surrounding two comets might have been the source. Astronomers, including members of the original Big Ear team, dismissed this. The comets weren't in the beam at the correct time, and comets don't emit strongly at 1420 MHz anyway. In 2024, a team using data from the Arecibo Observatory published a preprint arguing the signal might have been caused by a rare astrophysical event, a stellar flare energizing a cold hydrogen cloud, causing it to surge suddenly in brightness. That would explain why it happened once and never again. It's plausible. It's also unconfirmed. The signal has been searched for more than 50 times. Robert Gray looked for it using the Meta Array in 1987 and 89. Nothing. Gray searched again with the Very Large Array in 95 and 96. Nothing. SETI League tried in 95 with the Green Bank telescope. Nothing. Others have tried since with increasingly sensitive equipment. Nothing. Eamon had a line I keep coming back to. In a 1997 paper, he wrote, "I resist drawing vast conclusions from half-vast data." That's the honest truth of it, isn't it? We have one data point, 72 seconds of signal from nearly 50 years ago, no repetition, no confirmation, no explanation that fully satisfies. Just a printout with a word scrawled in the margin by a man who saw something extraordinary and had the honesty to say he didn't know what it was. The WOW signal didn't change physics, it didn't confirm alien life, it didn't even repeat. What it did was something quieter and maybe more important. It made us take the question seriously, not as science fiction, not as fringe speculation, as a real measurable, testable question about whether we're alone, and the answer, after 50 years of listening, is the same as it was on that Tuesday in August. We don't know. The signal came. It left. And the sky has been quiet ever since. Maybe that silence is the answer. Or maybe we're just not patient enough yet. Thank you for watching and sticking till the end. We've got plenty more videos coming in the future. Hit that subscribe button so you don't miss them. See you in the next one.